To the cloud.
Post a link that we have many of.
Pardon?
Can you post a link to the Zoom meetings? On just, yeah.
Can you? Because it's on my.
It's literally just www.
Okay, let's do that.
Just
Okay.
copy the link from.
Now we're recording.
Copy it from previous.
This is Tesla Dave. He's going to tell us
Trying
about some Tesla coils and high voltage electronics.
David Qualls, alias Tesla Dave. Website's at www.tesladave.com. And I got started in high school making Tesla coils. I went to Whittier High School. Got my novice ham radio license, had to have code back then. And my science teacher, my physics teacher, challenged me and asked me to do a paper on Nikola Tesla. I was a sophomore. This is the year of 1956. And so I went to the library and researched Nikola, and I got his patent. He patented the coil in 1891, and I tried to reverse engineer it. And for the secondary coil, I went to the linoleum guy and got one of his 6-foot linoleum rolls. It was about 4 inches in diameter, and then shellacked it. Back in the day, we didn't have, polyurethanes like we have now, better sealers for Tesla coil, polyurethane. And then I wound 800 turns on it, number 24 magnet wire. And that was hard, so I set up like a small lathe, had some help, and wound it, and I got halfway and I relaxed to have a Coke, and it all came unwound and I had to start over again. So if you're winding your own Tesla coil, have masking tape, and wherever you stop, you put a piece of masking tape, and then resume again. And it has to be wound tight, and it cannot be wound with one turn overlapping from the other turn. Anyway, to make long story short, I used glass and tin foil to make the capacitor, and it arced over. So being ingenious, I got some high voltage oil, which at the time was called castor oil, used for other things, but worked good as a dielectric to keep me from arcing over. I used a neon sign transformer, which this one has in it. It's a 12,000 volt at 30 milliamp as the primary, wound the secondary, and it worked. I entered it into the science fair. I got 3rd place, and they wouldn't let me turn it on. The high school says, we don't have liability insurance for this. We don't know what it will do. And that's why we're going to have the Tesla show outside, because just in case I see, about 50,000 or more, probably 100,000 in test equipment up there. So Tesla coils are bad. Does anyone have, I have to ask this, does anyone have a pacemaker? Okay, just had to ask. It destroys pacemakers. All right, so so every year I build a new coil, and I'm going to pass out some of the coils that I have built. My latest coils draw over $2,000 each. One sold for $2,400. To get people to buy Tesla coils, I designed what I call a steampunk Tesla coil. Does anybody know what steampunk means? It means stuff from the locomotive era, 1850s roughly to 1900. Old gauges, old, early, meters, anything that vacuum tubes came later. So this guy has a couple of vacuum tubes back here. It has an old pressure gauge hooked up. Couple of Tesla medals, picture of Tesla. The volt and amp meters work. Got a pilot light, a key, and a safety switch. And what I did, I sold this one for my second one, Sparky 2. I sold this one for $2,100 to somebody on eBay that had to have it. And I gave him a copy of my copyright because I copyrighted it as Tesla Coil Art. And this made it a unique product. Am I interested in making money? No, I'm just doing it for the fun. So here I am in a video, and I couldn't bring, I don't have any audio visual because of short notice, so I'm sorry about that. But here I am running it in my house, and it's pretty gnarly. It makes a lot of noise, and of course, I'm what, 3 or 4 feet away, and the fluorescent tube is fully lit. So you can use these to light fluorescent lighting or whatever you'd like. So I'm going to pass them out. This one started with a steampunk leather overwood case, treasure case. And I show you how I laid it out, and I put meters in front, drew where I had to drill, started packaging it. Transformer goes in first, spark gap. All Tesla coils have to have a spark gap. And here I am on my workbench, got all my wire strippers and soldering guns, putting it together. Here it is completed. And this one got $2,300 on eBay, and it sold like that. I could have made 100 of them and probably sold them all. And then here are some of my coils. This is Zeus, 6 foot. I sold him for $5,000 on eBay. This is a copy of Zeus output. This is Colossus. Colossus output, 15-foot arcs. You can tell on a discharge when it hits ground. The arc goes from purple to white, indicating high current. So if it hits ground or a person, the arc will go white, and the person won't be killed, but he'll be burned very badly. This RF just likes to burn protein, and of course, your skin is protein. So now Colossus is at my house in Grover, and I'm going to resurrect it and find it a home. I'm going to donate it to a university or a museum or somewhere. I'm not going to sell it. I sold it on eBay in 2006 to a multimillionaire guy, eccentric guy, for $10,000. And I would have sold it for $5,000, but he was bidding against another guy and they wouldn't stop bidding. And I said, well, and then he hired me back to hook the coil up and run it for shows. My biggest show was 300 IEEE engineers. And he brought them 50 at a time in on buses. And so I did 10 shows that night, each show 10 minutes, showing off Colossus in this very factory here. This is the guy's factory. You can see people in the background taking pictures. And not only did I demonstrate it, but after I answered their technical questions, told them how it worked, a little bit about how I built it. To wind this coil, I hand wound it in my backyard. Took 4 6-packs of beer to get through it. It was a hot day. Anyway, this is a parlor coil I made out of a oak holder for CDs. You guys probably don't remember CDs. They've been gone a long time. Anyway, so I got everything inside there, vertical, transformers, spark gaps, everything. And I still have this one that's in Grover now. This is another coil I still have that caught my garage on fire. It caught the ceiling tire on the ceiling tile, the plastic cover on it started blazing. So I had to stop the Tesla show that day in the garage. And so I'm going to pass all these photos out. Sorry, I don't have audio visual. Take a look. One of the things unique about Tesla is he was born actually in Serbia, in Croatia, on July 9th/10th, the year 1856. And why am I saying 9th/10th? Turns out that he was born during the stroke of midnight, and the history books show that there was a storm hovering above the hospital, and that lightning was striking and thunder. It was raining hard, and that he was actually born just I think 20 or 30 seconds past midnight, which makes it 10. So July 10th is his legal birthday. It's quite interesting. Tesla's father was a ordained minister, a priest actually, and his mother was a very sharp inventor for the day. She invented what would be considered to be household appliances, electromechanical, mostly mechanical. And they say that his actual IQ came from his mother, but you know, that's a moot point and kind of hard to prove. But nevertheless, he came to this country and couldn't get a job. And Edison heard about him and the fact that he was a visionary. He would think outside the box. So he would visualize a rotating motor. And he said, why couldn't the motor be a generator? So what do I have to do? So he woke up the next day, drew it all out. And lo and behold, he invented the first AC motor, an induction motor with rotating coils. And he also figured out how to do the slip rings, which is very ingenious. But he could visualize it, put it on paper, build it, and make it work. And so he did that for 278 patents. And it's kind of interesting because the first one that he did was in 1891, and that's this one here. So in 1891, he invented the high voltage generation coil, high frequency resonant rise coil that was named after him, called the Tesla coil. Well, guess how many things the Tesla coil became? Back in my day, there were no transistors. I had to learn tube theory. My first radio was a 6L6 Pinto tube oscillator with a plug-in, big fat plug-in crystal on 40 meters, put out 15 watts. I figured out how to get 25 watts out of it by turning it upside down, getting a metal tube. They made a 6L6 metal tube, putting it in a coffee can of water. Then the water got hot, so I got a fish pump and started pumping water in and out of the coffee can, and I was running 25 watts on 40 meters with a 6L6 tube. And I just rebuilt that radio, that transmitter that I had on a breadboard. I was going to bring it tonight and I forgot it, but it's quite nostalgic. I built that in '53. I got a novice license at the age of 14. 5 words a minute code required to get the license, and I was only 14, so I've been in ham radio a long time. So this became the high voltage generator, was a Tesla coil for the early TV picture tubes called a CRT. It's a cathode ray tube, and cathode ray tubes needed plate voltage about 1,000 volts per inch. So if you had a 12-inch TV, which is very common in the 50s, you needed 12,000 volts DC. So Tesla coils generate AC, so they figured out that they would wind this high voltage transformer on a piece of steel, which later became ferrite, to give it permeability, less turns, more inductance, higher voltage. And they use an oscillator tube to excite it. And then they used a 1B3 vacuum tube to change it to DC. So we changed the AC to DC, and they had a plug that plugged into the side of the CRT for the plate voltage. And it's quite interesting, all the old oscilloscopes, you know, it wasn't until years and years later that somebody invented the LCD screen. But so that was one use for the Tesla coil. The other use for Tesla coils were at universities where they had a collider. Collider is used to spin up electrons faster than the speed of light. That's right, faster than 186,000 miles per second. Usually you need 5 or 6 mile tunnel underground to do this. And about 50 million volts. So they would use Tesla coil in the early days to get to 50 million volts. You didn't need much current, but you sure needed the voltage to spin up the electrons and have them bombard a isotope, or have them bombard an element to create another different element. And so a lot of universities did that. Berkeley did it underground years ago and came up with one of the periodic table elements called berkelium, was generated up at Berkeley University. The other university developed something that the military is using in bombs. And at Princeton, they generated a particle that's very sought out called tritium. And tritium is a lot like strontium and some of the other radioactive materials used in nuclear bombs. So Tesla coil high voltage is more than just an ozone generator, because it does ionize the air coming off the wings here. You'll be able to smell it even outside. You can smell the O6, which is ozone. And are there any questions at this point? Anybody out there have a question on anything? No? Okay. Then would you like to learn how this thing runs, how it operates? It operates, as I think I was talking to you early, this primary coil comes from the spark gap, over here. So you will see sparks running up and down this spark gap. And the primary is tuned by this 0.012 capacitor. And this coil is tuned to 165 kilohertz. So it's not very high, it's low frequency. 165. Colossus is 88 kilohertz, about half that. It's much bigger coil. So how do we tune the primary? We tune this primary by measuring its inductance and the capacitance. And so the resonant frequency, so the frequency at resonance is equal to 1/2 pi the square root of LC. I need an eraser. There we go. So, so we have measured inductance, we have accurately measured, and so we come up with the primary equal to, what did they say, 168, I believe it was, kilohertz. Now, in order for the Tesla coil to work, we have to tune the secondary to that same frequency. Oh, great.
Here's my razor for you.
Oh, great. So now we have to make this coil tune to 168 kilohertz. What happens if we miss it by 20 kilohertz? Won't work. No spark, no output. Got to be right on. So how do we tune this one? Well, we know the inductance and the capacitance, and this top hat becomes the capacitance. Without the eagle, I don't make it a perfect tune without the eagle. What I do is tune it under, and when I put the eagle on, the capacitance goes up and the frequency goes down. So I actually tune it for 172, I think it was, put the eagle on and it comes back to 168, perfect resonance. And we're in tune, the primary frequency tuning, and I mean, the secondary tuning is equal to the primary tuning. And so it just puts out beautiful spark. It puts out a purple spark. Oh, wow. So once we match these guys, we get full output. And how do you calculate the output? Well, the input power is P is equal to IE. I have power factor correction in this transformer, so it's pretty close to 1. So the kVA and the kilowatts are equal. So on the phasor, what we have is, this is resistive, and this is X, and so the power factor, which we calculate, is equal to the cosine of the angle theta. So what we're going to do is have a vector that is going to measure where that is. In other words, we're going to measure the angle theta of the L. And the reason I use the L is that just about all power lines are inductive. Factories have motors. So the load is inductive. And so because it's not resistive, we have KVA. So if everything was resistive, KVA would equal KW because the power factor would be 1.0, which is very cool. So we're actually getting cheated by living near factories and getting power to our house because that's like 0.8. So 0.8 power factor inductive is what you see. So if you were to calculate the capacitance, the X of C you would need to add to your house, you would pay less power. So you would be getting close to resistive and there wouldn't be any offset or any losses. So it's kind of interesting power factor. If you work with three-phase power, most factories have 480 volts AC, three-phase. And coming into our house, we have off of a power pole, we got 15 kV. And we have a transformer coming off called a pole transformer. And the pole transformer puts out 240. And the center tap comes into the house for 120. So from here to here is 120, and from here to here is 120, and across here to here is 240. So what I did for Colossus, I bought one of these pole transformers and I'm hooking it up backwards. I'm putting 240 in and getting 15,000 volts out to run Colossus Tesla coil, which is, you know, good thing. The problem is it cost me $500 and it weighs 275 pounds. But other than that, it's a good power source for a Tesla coil. And so, but factories with 480, they're using voltages. So the voltage output would be the square root of 3, because 3-phase. And so square root of 3 is what, 1.732, I think. Don't quote me. But yeah, so you can calculate the line-to-line voltage. And it's quite interesting. Motors run from 480 at big amps because the cabling and the copper wire used to hook everything up is much smaller. So there's a big savings there. And all right. So how did I design this coil? I designed this coil using Java TC. This is a Tesla coil program that I bought for $50 24 years ago. This is a lot of money. I still use it. It's fantastic. And if you look at it, you tell it the parameters. You tell it the diameter of this coil and the length, and you tell it the frequency you want, and it tells you how many turns to put on. It tells you how big to make this, the diameter, to tune that. Same thing for the primary coil. It'll tell you for this coil, you need 8 turns and 0.012. That's all here in the program. Saves me a lot of time of trying to calculate it, you know, by hand. And I still love to do calculations by hand, but I now use Google. Have you guys have fancy scientific calculators? Don't need it. There we go. So let me throw a question to Google. This is one of my equations I use. What is 2 pi times the square root of 2 divided by 3.33? Oh. What is 2 pi times the square root of 3 divided by 3.33? There we go. That's correct. And I don't think you heard her from the speaker because I have my Bluetooth on and she read what I quoted. So yeah, so you can do math, you can tune your Tesla coil using Google if you want. Quite interesting. So I'm going to pass around this guy, and every parameter you would ever want to know is here printed out for you. And you can make adjustments. You can tell it, well, oh, what if I take 50 turns off of this coil? And they'll say, oh, if you do that, the frequency is going to move. It tells you what it is, and you need to retune this guy. And so it's a pretty good program, actually, still today. Does anybody have any questions about the tuning?
Well, that's the best thing about tuning, but if you bring the power in from 60 cycles per second,
Yeah.
how do you kick it up to the like 168 or whatever?
Oh, how does the frequency go up? Yes, that's a good question. By the way, one of the things that makes a Tesla coil have output at a frequency is the tuned circuits. This tuning, and especially the primary tuning. So this is tuned to 168. Now, how do we get there? We get there by this spark gap. So the AC is making and breaking. When I turn this thing on, you will see the sparks go up and down. I have a fan blowing it. And so what happens, so, whoop, there we go. What happens is, so we have the top hat. We have the secondary. It's grounded. Then we have the primary, which is those 10 turns at the bottom. Now, the winding is called heliax. This is heliax wound. And you could wind the coil up, have copper pipe or PVC coming up and wind it around the PVC this way. It doesn't care. The coupling's important. If you get the coupling too tight, it'll burn a hole right through the coil. So you know you overcoupled. But the primary is 8 turns on that one. And what it does is it has a capacitor across it. So this is the L, this is the C. And this combination must be 168 kilohertz. And the computer program told us how much L we needed, and I put that in, and it said the C here has to be 0.012 microfarads. So now we've got that tuned. So now how do we make this guy, the output, be at this frequency? So what we do is we put in 1, 2, 3, 5. Okay. And then we have a neon sign transformer here with 120 volts in. And this output is 12,000. So we will then connect this guy and this guy. And so now 12,000 kilovolts. Sorry, guys, kilovolt. 12,000 volts is going through 5 spark gaps, which are these guys right here. And they're sparking like crazy. And every time one of these guys sparks, I blow it out with this fan, and it blows out at like midpoint or close to the top and then restarts so fast your eye can't see it. And so I got a rep rate, and so it's called quenching. And what is quenching? Quenching is blowing out the arc so that it creates a spike, a repetitive spike with fast rise times and very fast fall times when you blow it out. If you do this coupled, you're inducing very, very high voltages into the secondary, which will produce, the arcs coming out of this guy. And so we have a series of pulses, which are, yes, 60 hertz. But the rep rate of blowing it out and restarting it is how we get it to tune to the LC frequencies that we've established here. And this is the C and the L. And the same formula applies 2 pi divided by the square root of LC 1 over. So I simplify it, I get rid of this, I get rid of this, and it becomes the resonant frequency is 0.159 divided by the square root of LC. So, yeah, we have a go. I might be going too technical or not technical enough. Yes.
I think this is perfect, technicality wise, but so I'm curious, how do you accurately control the frequency? Are you just designing a system and then are you measuring it afterwards and then doing your calculations? And blowing it out are you literally using the fan to blow on the spark gap to?
Yes,
Okay,
I'm using the fan to blow on the spark gap. I have put holes up here, big holes underneath here, so that there is no back pressure, that we've got laminar flow air coming out of this fan, which is a high velocity muffin fan, higher than most. And so by blowing this guy out, we get fast rise times, and the rep rates are pulsing this guy over here, forcing the LC to tune. So the only thing we have to make sure is that the tuning of the primary LC is the same frequency as the secondary LC. And if we do, we'll get maximum transfer of energy, which could be 1,000 times more. So we have, I forgot to tell you how many turns. Tesla coils are 650 to 800 turns. And why that number? Because all Tesla coils have to be tuned to 1/4 wavelength, which is what, lambda? Yeah, that guy. So it has to be 1/4 wavelength. Or it won't work. So if you make these turns 700, 750, 650, the computer will then tell you the capacitance value to tune to 1/4 wavelength, and it'll tell you the frequency. Now, when I look at the computer program and I look at the output frequency with a freq meter, it's a little bit different. It's not exactly as the computer model, but who cares? Because it wouldn't work if this tuning wasn't the same as this tuning. It has to be the same. That's the key for anybody building Tesla coils, is they're easy to build. You got certain safety features. For example, this is a spark arrestor safety gap. And this is ground, and this is one side of the neon sign transformer, and this is the other side. So if any voltages come back into the transformer, instead of blowing the transformer out, it'll arc over the ground, saving the transformer. Without that gap, you won't last 5 days and you'll burn out your neon sign transformer. So there's certain safety features you have to build into your Tesla coils to make sure you protect this guy. These things have gone up. They're like hundreds of dollars now. People found out that, okay, you don't need them for lighting neon lights anymore, but most certainly the Tesla coil builders use them. I found an alternate source for my steampunk because these are too big to fit into my small design. So I'm using a furnace transformer that's used across the US to generate a spark, so that when the thermostat says to turn on your heater, instead of using piezo, they use these transformers and a small spark gap to light their furnace. So, but any other questions about the tuning? So resonant rise, high Q, a good spark gap with air blowing on it. Now there's other ways to quench. I remember I said quenching is blowing out the arc and creating a fast fall time. It's this fall time that you need to be fast. You don't need it to be heat. No. You've got to blow that arc out. It's called quenching. The other way to quench is electromagnetic or permanent magnet. And you can set it up where the arc will be quenched by an electromagnet, which you can set up with a synchronization circuit, like to sync it to 60 hertz. And it will look at 60 hertz rise and fall and quench at the right times. So you would want to quench it as soon as it hit the peak of the cycle, then you quench it and it falls. So there's a lot of ways to do quenching. For Colossus, I used a 120-mile-an-hour weed blower on 4-inch diameter copper pipe separated by 0.2 of an inch each, 4 of them. And then I found out that I used a variac to adjust it so that I got the best output, and I knew that the best output was the right amount of air to quench that spark gap by adjusting a variac on a cheap weed blower.
Yeah, so with this design of the spark gap, does the velocity of the air matter a lot? Does the distance of the gap matter? And then are you, so I'm trying to figure out how you design this, because it seems like you couldn't get, like you couldn't design this in such a way that when you're finished building it, you know immediately what frequency it's going to produce.
Yeah,
Do you measure it and then design the coils to the frequency that
No.
your system outputs? How do you
no,
know?
you probably haven't got it yet. You use the Tesla design program. There's like probably 10 or 12 of them out there. And it's a proven design that's taken from the top Tesla builders. Like, I'm like number 3 builder in California. And each state has Tesla Coil Builder Society or club or whatever, and they turn in their designs. Okay, here's a proven design. It's 24-inch diameter. It has 800 turns of number 18. It has this inductance. It has a 6-foot diameter by 14-inch aluminum dryer duct toroid. So what you do is that you make these toroids, instead of when they get big, to spin. This is called spinned aluminum. It's 2 half shells put together, and it's done on a big lathe. It's a very expensive process. So for Colossus, I took a 12-inch diameter dryer duct. I took one of these aluminum trays that goes under your water heater. So if your water heater bursts, this tray will catch the water, and it has like a PVC coupling to go out through your garage or whatever. And I used that, and I made and tuned the torus. And how did I know how big to make it? Computer program. Because without it, you'll spend months trying to figure it out. So proven Tesla coils, that data has got into Tesla coil programs that are proven to be, if you follow what they tell you and design it in that Tesla coil program, it's going to work. So, yeah, it takes the guesswork out of it. You know, it saves you a lot of time just using the computer program. I'm sorry.
The frequency, right? What do you want your ballpark or frequency to be like? What can it be?
Okay, here's the thing. What color arcs do you want? The higher the frequency, the more purple. It's proven fact that coils that run from 65 kilohertz to 90 kilohertz are the biggest sparks. And the reason being is, to get to that lower frequency, you have to, because you know it's going to be 800 turns, 700 turns, you use bigger diameter wire. And so the spark diameter of the discharge off the torus coming out is bigger diameter, bigger lightning bolt. So if you want something that looks like corona discharge, you know, 300 kilohertz. Some of the solid state coils, which I don't build, are very expensive because the transistors, the power transistors, it looks like they're using IGBTs. As does anybody know IGBT yet? What it is a integrated gate bipolar transistor. So what it is a transistor. It could be a PNP, or, you know, I'll draw an example. This is a PNP. And then what they do is that they have an IC in here, that drives it. And so now you can hook up a signal generator with a 1 volt square wave and drive this transistor, and it may have a 2000 volt at probably currents in excess of 100 amps. These are big blocks, and that block is an integrated gate bipolar transistor, so it has an IC in for driving the power transistor. And I've got a couple of them, and I've never bothered to make, I'm capable, but I never bothered to make it because I love the arcing and sparking of the old 1891 coils. So
For like just a quick question about using transistors. So if you're changing the frequency while the coil is operational, doesn't that mean that you would also
you won't,
mess with the resonance?
you would never ever change the frequency with the coil operational, never. It's set, it's locked in.
Okay.
So how many gaps you have on the spark gap? The computer calculates, that's 5 gaps. It calculates the L's and the C's. And it tells you, okay, you've got to take off 2 turns, or you've got to add a little bit here. It tells you, the computer program tells you what to do. And once you do it, it's locked in. You don't ever mess with it. Now, I do change the frequency of Colossus while it's operating, but I do it because I have a rotary spark gap, and I was going to bring it. And so I have a motor, and this motor is turning a wheel, and the wheel has 6 tungsten electrodes. So there's 6 of them rotating. I'll show 2. Each one of these electrodes is 1/2 inch diameter. Okay, and so I'm running this guy from a variac. Okay, so this guy is variable so that I can change the RPM, and I run it from I start at 1,000 RPM, and I run it to 7,000 RPM. This wheel is 1/2 inch diameter G7 military fiberglass wheel. Glass epoxy, very smooth, no rough edges, balanced, turned on a lathe. The wheel for Colossus cost me $200 to make. The electrodes are $25 each. Colossus is running with the pole transformer, it's running 30 kW. What is that? That's 15,000 volts into it is equal to ID. That would be 2 amps. And I have a way of regulating the input inductance so I don't exceed that rating. If I do, and I go higher amps, I burn out these 1/2 inch diameter pure tungsten, which is, about the highest grade electrode you can buy for a spark gap is tungsten. So what happens when I get to 7,000 RPM? So here I am running Colossus, or running this power through this spark gap into 1 inch diameter copper tubing, 6 turns around Colossus. The secondary is 800 turns of number 16 gauge wire. Because of the diameter of Colossus, it took 2,800 feet of wire. So I had to make sure that I bought a spool that had no splices. The nightmare for a Tesla coil winder is to get halfway through and there's a splice. You're dead, you know, throw it away, start over. Anyway, so my point is, how do I change the frequency of the coil? The output frequency I don't change, but guess what this rotary spark gap does? Because I have 6 electrodes at this RPM, the output is approximately 600 hertz to 2,000 hertz. So I'm modulating by the spark gap RPM. You can hear it. You can hear it go up, and when I lower it, it goes down, and people are looking around when I'm running Colossus and I just crank it all the way up to 2,000. Why do I stop at 2,000 when the motor can go to 10,000 RPM? Because I will blow out the capacitor. Now, this capacitor was $50 used on eBay. Colossus capacitors are 2 big laser capacitors. Huge. Each capacitor is 20 pounds. Okay, and what I do is I hook them in series. And okay, so this is 0.44 microfarads. 0.44 microfarads, 50,000 volts working. kVW. So the working voltage of these laser caps, by the way, they cost me, what they pay, $250 each. I got the pair for $500, which was cheap. So building big Tesla coils is expensive. Start with this. Anyway, so let's see. Capacitors in series is 1 over a total 1 plus 2. So the output is 0.22 at 50 kV. So capacitors in series is 1 over. Yes. Tell me if I do the math wrong.
No, that's right.
It's been a few years. Okay, so I now have a 0.22 microfarad capacitor at 50. Oh, yeah, geez, you didn't catch me. The voltage doubles, 100,000. Voltage doubles in series, 100 kV. Somebody should have caught that. So half the capacitance value in series, you double the voltage. So you can buy small caps and put them in series and maybe save money instead of having just 1 cap, if you have the room, only if you have the room. So yeah, so having the ability to change the spark gap speed does not change the output frequency of the coil. That is set. It does modulate the coil by the audio component that's generated by the make and break. As I said, 2,000 breaks per second would be the same as 2,000 cycles per second, and we now say hertz. It was the hardest thing for me to go from tube theory to transistors when they came out. So I had to learn whole flow theory. Oh, the holes the holes are moving this way and the electrons are going this way. Oh, the holes are positive. Oh, and then you had to remember what year you were in, to what theory was. Because in the old days, electron flow and current flow were the same. You know, negative to positive. And so things have changed over time on what the theories are, but it all works the same. Any questions so far?
So this is what you would hook up to it if you wanted to change, if you wanted to produce like audio from
Now,
from the thing.
spark gap Tesla coils, the disadvantage is you can't modulate them with audio.
Not even with a rotary spark gap?
No, no. I tried it. There's a modulation technique we used in the sixties called Heising modulation, where you actually took a big audio amplifier, much bigger than you needed. You know, like a 200-watt audio amplifier. And for protection, you use fiber optics to couple it, because you wouldn't want to blow it up with the Tesla coil, so you need to isolate it. And then I thought, oh, so the power going to the Tesla coil, okay, out of this guy. So why not put a transformer in here? And then use caps, and then have a big audio amplifier driving it. You know, so you've got a big, whoop, wrong way. So we're gonna drive this guy. And then so this guy's 200 watts, then you got a preamp on here, fiber optics, whatever protection. And so I tried that. Wouldn't work. Wouldn't work. So I know of no one in US history that has modulated a spark gap Tesla coil. That's why you need a carrier, which is like a solid state Tesla coil. It's more like Class C oscillator. You know, it's not even a Tesla coil, actually. Tesla would roll over in his grave. Anyway.
Is it kind of like an AM radio where you have like a
I'm
carrier?
sorry.
Is it kind of like an AM radio or like radio where you have a carrier and then you're modulating a signal into it essentially?
Yeah, it's
Okay.
it's like a CW transmitter, and that's running Class C and solid state. And then you build a Class B or AB amplifier, which is linear, to drive it. And you use a transformer called a plate transformer, but right now it's a collector transformer to drive it. And then you have AM modulation. So you can AM modulate, but they modulate it with more than AM. They use square waves and pulse shapers, and they get different sounds out of it. And then they write a computer program to make it play music. And so you see a lot of that, two Tesla coils arcing at each other, playing, you know, some tune.
What determines the number of spark gaps you need?
The spark gap, how many, what? I'm
How
sorry.
many spark gaps?
Oh.
Like, what determines that?
The what determines it is your space, but two spark gaps works marginally. 4 or more is ideal. So I put 5 on this one. More than 5 or 6 is no gain. But having just 1 gap or 2 gaps doesn't put out a lot of output.
So it's not sharp enough?
Right, it's not enough rep rate. In other words, I'm blowing these things out with this air, And when I first started, I put a variac on this guy separate from the voltage variac. You always bring a Tesla coil up on a variac because if something doesn't look right and the spark gap doesn't sound right, then, you know, it's dangerous. Just to turn one on, you could burn everything up in one surge, you know, fry everything. So you always come up slow. If, is there any other questions before I demonstrate? I'm going to do a live demonstration of the ultra, they call it the high frequency violet ray. And let me stop for questions before I go any further. Anybody else on coil? Yeah.
Sorry, are the spark gaps in series or are they, or do you turn it off? I'm trying to understand like how that. How it works, yeah, well, yeah, like, is it just like they successively, spark when they're in series, or would it change?
The spark gaps are always in series. Yeah, and I wished I could turn it on in here, but when we take it outside for the demo, you're going to see a bunch of dots moving up and down between each of the 5 gaps. And there's no synchronization because your eye couldn't track it as fast because the air is blowing it out, quenching it. Quenching is causing a quick fall time, which is coupling massive amount of energy into the secondary, producing the high voltage.
Yeah.
So just make sure if you build a Tesla coil, you have 4 gaps or more. 6 is okay. The diameter of the tubing is based on the power, which is the heat. So the output is 12,000 volts at 30 milliamps. P is equal to IE. So the 30 milliamps, that's 360 watts of power. If I want any smaller, they get hot. They get so hot that the fan cannot quench the gap. We cannot produce a quick fall time. We cannot transfer maximum energy from primary to secondary. So it's really important to look at how much power you're running. And that's why we use the computer program that I passed around, which is the guiding thing for proven Tesla coils that have been submitted to the guy that wrote the software. So his program is based on proven values in many Tesla coils. Yeah.
How much does humidity like affect sparking?
A little bit, yeah, yeah. You know how we measure calculate the output voltage? With a wooden long yardstick. In fact, I glued, for Colossus, I had to glue 5 yardsticks together because it had 16 feet of purple corona coming out at 88 kilohertz. That beautiful spark until it hits a ground pat, and then it turns white because of the current, as I told you. Once you start pulling current off that toroid, things go from purple to white. So it's a good indicator you're hitting something that's grounded, hopefully not a person.
All right, let's pop outside and then we get into some more questions after.
Okay, before we go, is it okay if I turn on this device?
Yeah, go right ahead.
Yeah, it's harmless. I just want to show you quack medicine from 1925. The claims are that this device will cause hair growth. Now, whoa, okay. So this tube is the hair growth stimulator. And what it does, they say, is bald spots you do like 10 or 15 minutes of treatment before bedtime. And it's all good to go. So just to show you what the output looks like, this is a Tesla coil inside, made in 1925 by some quack doctor. And it is UL. So that's the only reason I'm plugging it in here, is it is UL. Whoa, now if the lights were out, you would see it really is violet ray. And yeah, good old Tesla coil. Now, here's the trick, is to get it on quick so it doesn't arc to your skin. Ah, oh. Now, if anybody wants to come up here, you can feel it really good. Anybody, do I have any volunteers?
Yes.
Okay. All right. You feel it?
Yep.
Now, I'm not responsible if hair grows on that,
I got enough hair already.
but anyway, it's fun. Ooh, I don't know how they do that. That's almost like a variac built into that thing. In 1925, this guy was ahead of its time. Anyway, quack medicine, Tesla coil, Tesla's invention. All right, are we ready to move the coil?
I got it.
Yeah, let's. Photos up for you.
Yeah.
You want it open?
Yes.
Somebody might be able to carry it out, or,
Yeah, I can carry it.
I put the eagle back on?
Oh, yeah, sure, for sure.
hey, hold on. I was gonna have you put this on your wrist,
Ah,
and then all,
light it up.
all these would light up from the gadget.
It's nearly dark, so we're gonna get some.
We'll get some good visuals.
Yes.
some visual aids.
You guys had some good questions.
We're pretty close.
Super.
Out of this group, we might have one.
Do we wanna
record?
I mean, I don't know how well it's gonna record.
With a case.
I would love it.
I mean, you're
We
probably
just
to it
have
a bunch of
to-
keys.
Yeah.
Later.
Yeah, I can give you a
Okay.
lot of the parts. I have
Uh,
some of the parts,
yeah.
as you know.
Really?